So we left off at the end of last week talking about graphing lines and slope. And we had graphed simple lines like y equals 3/4 x minus 2. And there were two parts of that line that we could get straight from the equation when it was in that form. The equation had to be in that y equals form like that. And when it was, we could pull out the number that was added or subtracted. In other words, the number that's away from the x. And that was what we called the y-intercept. And most importantly to us, that's where we start. And we start on the x-axis. So from our origin, the center of the graph, we went down 2. So -2 there is where we started. And then the number that multiplied x, that was the slope. And that slope was a rise over a run. So from this starting point, from that y-intercept at -2, we would rise 3, because we had 3 in the numerator, and run 4. So our line went through those 2 points. If there wasn't a fraction in there for the slope, if we had y equals, and I'm going to throw a negative in there with it as well, -2x plus 3, well, that +3 or +3 is telling us from the center of the graph, from our origin, we go up 3, and that's where we start, right there. From that point, the slope is -2. We make it a fraction by making it -2 over 1. So that's saying we rise -2. So we go down 2. And then we run 1. So over 1. So that line goes through those points. Now, one of the difficulties here is when we're graphing, the first thing we do is go up or down. You know, we did the -2 here, we went down 2. Or the +3 here, we went up 3. And then when we do the slope, we do the same thing. We go up or down first, and then we go over to the right. But when we're plotting points, remember, if I have the point 5, 2, when we're dealing with those points, the first number is not up or down, it's the x. It's left or right. So that is saying to plot that point, we go over 1, 2, 3, 4, 5, and then we go up the 2. So it's exactly backwards when we're plotting points on the graph. So you have to be very careful with that. Then along with that simple equations, the slope and intercept, they have a lot of meaning into a real-life situation. For example, we might have a graph that looks like this. And we'll put time along the bottom here. So this is going to be time in hours. And this over here is going to be concentration in, let's go milligrams per deciliter. So let's say that this starts right here and goes I'm going to draw some shadows here just to, because my artwork is not that good. So let's say we have those points. So if I'm looking at this graph, first thing I might be asked is, what is the concentration at 3 hours? Well, here's 3 hours right here. I just trace that up to my line, and I trace that over, And I can see it's between this has got to be the 175 there. It's between 175 and 200. It looks to be almost exactly between. So we're going to call that 187.5. We don't know that it's exactly between unless we look and see that this is exactly on 150. This one up here is exactly on 225. And then we can tell then it has to be exactly in between because that line is because it is a line, it must go up with that constant rate. Let's say we are asked to find the y-intercept. Well, the y-intercept, as we mentioned last week, is the initial point, the starting point, where everything begins. So that y-intercept is right here, 75. And what that is saying, that's 75 milligrams per deciliter, what that is saying is at time 0 hours, or t equals 0, the concentration is 75. We might be asked to find the slope. Well, the slope can be found from any 2 points. I've got 3 points here, actually, that are clearly marked on this one, or clearly identifiable. So I'm going to do this one here. This one is 0.75. This is my y-intercept. And this point up here is 2 hours and 150. So I can get my slope from those points. I could draw in a triangle and do this, but I have to be careful because this is not one per space here. It's easier for me to get it from the points, 0.75 and 150. So my slope formula, I label those points 1 and 2, remember is y2, so that'd be the 150. That's 0.2, the y-coordinate, minus y1, would be the 75, 0.1, the y-coordinate, over, on bottom it's x2, so 0.2, the x-coordinate is 2, minus x1 was 0.1, the x-coordinate is 0. So here we have 150 minus 75 is 75. 2 minus 0 is 2. 75 divided by 2 is 37.5. Those units would be milligrams per deciliter per, the run is in hours, so per hour. So from this information, we can form the equation of that line. So if I ask you for that equation, it's y equals, the slope is 37.5 milligrams per deciliter per hour times x plus the y-intercept is 75 milligrams per deciliter. So that's the equation. And we might then from there be asked different questions of, like at number 5, we might ask, at what time would the concentration be let's see here. Let's look at 300 milligrams per deciliter. So I'm going to take that equation. Milligrams per deciliter is the concentration. So that's going in for y. The vertical is the concentration up here. So that would be the y variable. So 300 goes in there. I'm going to leave off the units to simplify this a bit. So it's 37.5 times x plus 75. And we just have to solve it for x. Subtract 75. 225 equals 37.5 times x. And divide by 37.5. So 225 divided by 37.5 gives us 6. So what that is saying is at 6 hours, the concentration should reach 300. Or a little bit simpler question might ask, what will the concentration be at 8 hours? So we have that equation still, y equals 37.5x plus 75. Now remember, x is the horizontal variable, and that is hours. So we're putting the 8 hours in for x. So 37.5 times 8 plus 75. Well, 37.5 times 8 comes out to be 300. 300 plus 75 is 375. That is milligrams per deciliter. Okay. Today now we're going to move on to a couple of new things. One of the things we're going to talk about is practical graphs, data graphs. And there are a few different types of data graphs we're going to talk about. In our next unit, when we talk about statistics, we're going to look at different types of data, and it'll become a little bit more clear why we use each type of graph in different situations. But one type of graph we use is to graph categories. So we're not comparing one number to another. I mean, what we've been doing so far with these is technically called a scatter plot. If we were looking at statistical data here, where you have numbers across the horizontal axis, numbers up the vertical axis, and you're plotting a relationship between two numbers here. That's not always the type of data we have and what we want to work with. For example, let's say we want to display here students in different programs. I'm not going to list individual programs. Let's list business, health, and trades. So that's the type of program, and let's list the number. Technically, the amount that are in each is referred to as a frequency. And let's say that we take a group of students. We'll just stick to the Rice Lake campus here to keep it a smaller number. Let's say that the business has 183 students. Health has 267. And the trades have 214 students. Looking at this table, there's only 3 different programs listed, 3 different categories listed. It's not that hard to look at this list and pick out which one's the largest number, which one's the smallest number. But if there were 8 or 10 of them there, it might be a little more difficult to pick that information out. So to make that process, that task quicker, we would use a graph. Now the type of graph we would probably use for this, I would recommend a bar graph. So I might put business, health, and trades, evenly spaced across the bottom here. And numbering up the sides, I have to number at least to my largest value. That's the 267 here. So I number this 100, so 50, 100, 150, 200, 250, 300. So I'm at least to the 267. And now I'm going to draw bars in here to represent those. So business goes to 183. So that's going to be somewhere in here. Health goes to 267. Somewhere in there. And trades 214. So now looking at this graph, I can very quickly tell that health has the most students and that business has the fewest students of these three categories. The weakness here is if I ask you how many students are in the trades. I'm going to grab this, I'm going to trace this over. And even if I do manage to trace that over perfectly straight, it hits the axis here. Well, this is 200 and this is 250. Is that 210, 215, 220? I'm not going to be able to get an exact number off this graph. On a test, if you're asked, what is the value of this category on the graph, I have to give you a 1 or a 2, either side, because it's not easy to get an exact number. The graph is for that quick reference we mentioned. Finding the largest or the smallest, or comparing two. If I ask which has more students, business or the trades, I can pretty quickly see, the bar for trades is larger, so there's more students in the trades. If I want an exact number, though, the graph is not a good tool. I go back to the table. Now, we saw something, I mentioned it briefly last week. Something that we'll run into, and it has a good purpose, but it can also be very deceiving. I didn't do this very well, but I'll just slide down a little bit yet. Oops, come on. Gotta give myself a little more room here. There we go. There, made it work. So here I'm numbered all the way up to 270, so I can get my data on here. But you'll notice I didn't start at 0. I had this symbol on my axis. We mentioned that last week. That means that either we didn't start at 0 or we started at 0 and then made a jump at somewhere in our numbers. We didn't keep a uniform scale up through there. So business at 183 is going to look something like that. Health at 267. And the trades at 214. Now this does the big advantage to this is I trace this over. I at very least know that business is between 180 and 190. It narrows it down a little bit more. I still might not be able to get it exact, but I might be able to guess, 182 to 184 at least here. Maybe not exactly the 183, but I can get a lot closer than I could with this one up here. Up here, all I could say is somewhere around 180 to 190. It's in that range. But the big disadvantage to this graph is look at the comparison between business and health. It looks like health is like 4 or 5 times as much. And it's not. As this graph shows, it is considerably more, but it's not even double. So there's advantages to each type of graph. This one gives you a more accurate big picture, but you can't see the details. This one, you can see the details, but it can be misleading in the comparison between them. Other graphs that are important. You might have a pie graph, pie chart, or circle graph. In a pie graph, pie chart, or a circle graph, really the difference between a pie chart and a circle graph is the type of data that's in it. So we're not going to get too far into that right now. But the structure, the way they work, is pretty much the same. Let's say we're looking at the cost of going to school. We might say here that 56% is tuition. 19% is books. And the remaining 25% is living expense. That would include your driving, extra rent, stuff like that. You might be asked something like, for a student who spends $6,800 per year for school, how much is expected to go to books? Now, one of the keywords there is expected, by the way. We have to say how much would you expect them to spend on books, or how much is expected to be spent on books, because these are averages. Not every student spends 19%. Some might spend 8%, some might spend 30% on books. It's an average. But on average, how much do we expect them to spend on books? Well, books are 19%, so we go back to our percent calculations from the second week. 19% is 19 out of 100. How much is that out of the total of 6,800? Cross multiply and divide. 19 times 6,800 divided by 100 gives us $1,292 in books. The opposite side of that is you might be given a circle graph that looks something like this. And it might be like the breakdown of your classes. And let's say that in your program, you have 24 different classes you take. Of those 24 classes, maybe 8 are generals. 3 that are employability classes. You have professional profiles or anything like that. And 13 are your core. So you might be asked, what percent of the classes are employability? To do a problem, to answer a question like that, you have to find the total. Well, 13 plus 8 is 21, plus 3 is 24. So there's 24 total. We're looking for what percent? So it's blank out of 100. Employability is 3 out of the total of 24. We cross multiply and divide here. 100 times 3 divided by 24 is 12.5. 12.5 out of 100, or 12.5%. Final type of graph we're going to look at for now. What we've been looking at there has been graphs that are kind of a snapshot in time, showing us one value that has different categories, different possibilities, and how it's split between those possibilities at that single point in time. The next one is used for showing what we call time series. What time series is it's just tracking a single value, but over time. So we might be looking at tuition per credit. So what you would pay as a student for 1 credit at WITC. Well, in the table, let's say we have years here and the cost. And then let's say we'll go 2000, 2005, 2010, and 2015. Let's say in 2005, the cost per credit was $98, or sorry, in 2000, the cost per credit was $98 per credit. In 2005, it says $113 per credit. In 2010, it jumped up to $156. And in 2015, it was $148. The type of graph we make to show this is called a line graph. What a line graph does is it puts time, again, across the bottom axis, across the horizontal axis. So down here is going to be the year. And we'll put this here as year 2000, 2005, 2010, and 2015. Up the side, we have to make sure we cover the range up to the highest number. The largest number here is the 156. Now, just like we showed with the bar graph, we could start at 0 and number up, or we can have a little break in the axis like this. Our smallest number is 98, so maybe we'll start numbering at 90. So 90, 100, 110, 120, 130, 140, 150, 160. You also notice I don't always number every line. I can number every other one, every fifth one, whatever, as long as it's clear what each marking is on that axis. And now I can plot points. In 2000, it was 98, so 98 somewhere in here. 2005, 113. Oops, put that 98 in the wrong spot. This is 100 here. 98 would be right there. 2005 was 113, would be here. 2010, 156 is going to be somewhere up here. 2015, 148, somewhere in there. And we connect the dots. Now, a big mistake that a lot of people make, I should say, is they take this and they connect it down here to 0. That does not exist. There is no such, the tuition is not $0 at any point in the past. So that line would be meaningless there. We don't want that there. What the line graph does is just like a bar graph, we can say what year was the tuition the highest. Well, that's where the line is at the highest point. So yes, 2010 would be what's at the highest. But what a line graph is really best for, what it's intended for, is to show when is it increasing or decreasing. Well, here we can see that tuition was increasing. We can't tell the individual year because we only did every 5 years, but from 2000 to 2005, on average, it increased. From 2000 to 2005 to 2010, on average, it increased because the line is sloping up, positive slope in terms of our graphing. 2010 to 2015, on average, it's decreasing because the slope of that line is negative. It's sloping down. Now, again, because we're only plotting every 5 years, there may have been just one big year where there was a big drop in tuition and it's been slowly climbing back ever since. We don't know. We just know that on average over that period of time, it went down. We can also look at this and very quickly tell of the times that it's increasing, when is it increasing the fastest? Well, the line is the steepest right here That's when it was increasing the fastest. So those graphs are very good for showing really quickly what is it that, what's the relationship between these values, which one's biggest, which one's smaller, and going up or down. But again, if I wanted the exact value looking at this, if I wanted to know what was the cost of tuition in 2005, well, I'm right here. I can trace it. Come on. I can trace it over, but you can see there I can't tell for sure, is that 110, 112, 113, what's it at? Getting an exact value off the graph, again, is difficult to do. That's where we would go back to a table like this. Any questions? Okay. So the next topic we want to look at is we want to look at relationships between variables. We simplify most situations we look at down to two variables. In most cases, in almost every case, there are other variables out there that we have to ignore because we can't consider all of them at once. Sometimes there's 3 or 4 that we can consider together all at one time. But in most cases, we look at those two related variables and we assume that other values, other variables, are unchanged, or not changed. They stay constant. So that's a big assumption, and it may or may not be correct in some of the cases. So we're going to start out, we're going to look at relationships between two variables mostly. We might look at a little bit at some where 3 variables come in and how we can do relationships between 3 variables. But there are 2 main possibilities when it comes to relationships between our variables. There is what's called a direct relationship, or direct variability. And our variability, if we say that 2 variables vary directly with each other, I'm just going to call them x and y for now. What I'm saying is that the value of x gets larger, then the value of y has to also get larger. Maybe not the same amount, but at a proportional amount. Or, if the value of x gets smaller, the value of y will also get smaller. Again, maybe not the same amount, but a proportional amount. Inverse variation, or variability, what we're saying there is if one of the values, if x gets larger, the other value has to get smaller. Or, again, the other way around. If x got smaller, the y value would have to get larger. So kind of a balancing act. So let's focus in on that direct variability, or direct variation. So when we're looking at direct variation, we have some general forms of equation that we can look at. First of all, direct variation is sometimes referred to as a constant ratio. In other words, it's proportional. The ratio between the two variables will be the same, will stay the same. So what that means is the ratio of y over x is equal to a constant. One way of looking at it. A more common equation, other than the y over x equals a constant, a more common way of looking at it is this, that y is equal to a constant times x. It's a linear relationship. So if we are told that y varies directly with x, what that is telling us is y equals a constant times x. Y equals kx. Our equation takes that form. If we go the next step, y varies directly with x or directly as x, however you want to word it. And y is 42 when x is 14. Now there's two pieces of information here. First, y varies directly as x is still telling us that same thing. Y equals k times x, a constant times x. But then we also have this piece of information here. Y is 42 when x is 14. Well, it's a piece of information about this relationship, but it also allows us to find almost pretty much the exact relationship. Let me show you what I mean. Y is 42, so I put 42 in for y. That's going to equal k times when x is 14. So now I can solve that equation for k by dividing by the 14. I get that 3 is equal to k. So I can take that 3 and put it back up into this original relationship to tell me that not only does y equal k times x, but since k is 3, the relationship is y equals 3 times x. I might be told y varies directly with x, and y is 28 when x is 7. Find y when x is 9. So now there's two pieces of information still and a question or a request. We still have y varies directly with x. That still means y equals k times x. Our second piece here, y is 28 when x is 7. Just like before, I put 28 in where the y is. For k times x becomes k times 7. I put 7 in for the x. And I can solve now for k. Dividing by 7, I get 4 equals k. So that tells me, again, my relationship is not just y equals k times x. It's y equals 4 times x. Then the new piece to this example, find y when x is 9. So I can put 9 in where x is. So 4 times x becomes 4 times 9. excuse me, and I'm looking for y. So 4 times 9 is 36. Y equals 36. Any questions? So a slight variation of that would look like this. Y and x vary directly. And y is, oh, let's see here. Let's say y is 18 when x is 9. Find x when y is 14. So it still has the same three pieces to it. Y and x vary directly. That's the same as saying y varies directly with x. That's telling us y equals k times x. Y is 18 when x is 9. So I'm going to put in 18 for y equals k times, put in 9 for x. So divide by 9, 2 equals k. I'll take that 2 and replace k here to get a more exact relationship. Instead of y equals kx, y equals 2x. And now this part is a little bit different than the last example, but it's the same concept. Find x when y is 14. So this time we know y is 14, and we're going to have to solve for x. X is multiplied by 2, so we divide by 2. Get 7 equals x. Any questions there? We might be told y varies directly with the square root of x. Y is 24 when x is 9. Find y when x is 25. So this first step here, still the same, but there's one little twist to it. Y varies directly with the square root of x, which means y equals k times something. It's not just k times x anymore, though, because y does not vary directly with x. It's the square root of x. So y equals k times the square root of x. The next part is going to be the same. Y is 24 when x is 9. Put 24 in for y. Equals k times, inside the square root, we replace x with 9. Now there's going to be a couple extra steps to figure out what k is here, because we have to do the square root. So the square root of 9 is 3. Then we'll divide by 3 to get k by itself. Solve for k. So 8 equals k. So we can still put that up here in our original relationship to define it better. Replace the k with 8. So y is equal to 8 times the square root of x. And then finally find y when x is 25. Put 25 in there where x is. We have to take the square root of 25, which is 5. So it's 8 times 5, which is 40. So y equals 40 when x is 25. Any questions? We might end up with y varies directly as the square of x. Y is 48 when x is 4. Find x when y is 12. I'm going to try that one in your notes. Give you a minute or so to work on it, then we'll go over it. Okay, let's take a quick peek, then we'll take our break here. Y varies directly with the square of x. Means y equals k times x squared. Y is 48 when x is 4. 48 goes in for y. 4 in for x. Now again, to solve, we first have to square the 4 to get 16. So 48 equals k times 16. We solve for k, we'll divide by 16. You get 3 equals k. So y equals 3 times x squared. Now on this one, I gave you y instead of x. So 12 equals 3 x squared. You solve by dividing by 3. 4 equals x squared, and then you would have to square root. Square root of 4 is 2. I'm guessing most of you got 2. Did anybody catch that there was a second possible answer? Or negative 2 could be x. Square root of 4 can be 2 or negative 2. Now in real life, most of the time we're dealing with positive numbers. So that one most likely is not an applicable answer, but on a test or a quiz, that would be, or on a test, that'd be the one I'd be looking for anyway. Okay, a minute or two over for breaks. Let's go ahead and take our break. Let's come back at about 9:32.